right, so let's apply the angle sum identities to solving an equation. And sometimes it's as straightforward as doing what we did last time, but having an equal sign on the other side. Sometimes it's a little more convoluted. So let's take a look at this equation. Suppose I want to solve the equation sine x times sine 2x plus cosine x times the cosine of 2x equals square root 3 over 2. And you've got a mean math teacher who says that she won't accept an answer from Desmos, so you can't just plug this into Desmos and hit the intersection points, because she unreasonably wants to see your work. All right, so let's take a look at our angle sum identities. And what do we see? All right, so what I'm doing is I'm comparing the pattern that I see on the left-hand side of this equation, where I've got a sine times a sine plus a cosine times a cosine, and I'm looking for that same pattern on the right-hand side of my identities. And sure enough, I almost have it here. I've got a cosine times a cosine plus a sine times a sine. But I remember that I can add in any order, so I'm going to rewrite my equation to be cosine x times cosine 2x plus sine x times sine 2x equals square root 3 over 2. And so if I compare this to my pattern, I can see that x is in the alpha spot, because this is cosine alpha times cosine beta plus sine alpha times sine beta. And my angle sum identity tells me that this left-hand side of this equation simplifies to the cosine of alpha minus beta. So x minus 2x, which means cosine now, you can simplify what's inside your parentheses. Negative x equals square root 3 over 2. So you'll remember the negative angle identity, and you'll remember that cosine is an even function. So cosine negative x is equal to cosine x. We think about our unit circle. And we realize that cosine x equal root 3 over 2 means x equals pi over 6 plus 2k pi, or x equals 11 pi over 6 plus 2k pi. Okay, so you can see how those identities helped us to solve that equation. Sometimes we also need to split apart a function. So let's take this function, this f of x equals 4 times the sine of 3x plus pi over 3. And what I want to do is I want to rewrite this thing in terms of sine and cosine. And actually what I want to do is I want to add up I'm going to rewrite this as a sum of a sine function and a cosine function. So the first thing I'm going to do is I'm going to apply my angle sum identities. So remember what those are. The sine of the sum of two angles, sine alpha plus beta, is sine alpha times cosine beta plus cosine alpha times sine beta. So let's just write this down here. Sine alpha plus beta is sine times cosine plus cosine times sine. So that's sine alpha times cosine beta plus cosine alpha times sine beta. Yes. So that means that 4 times the sine of 3x plus pi over 3 is going to be equal to 4 times the sine of 3x times the cosine of pi over 3 plus the cosine of 3x times the sine of pi over 3. Now we know the cosine of pi over 3 is root 3 over 2. No, sorry. Cosine of pi over 3 is actually 1/2. Plus the sine of pi over 3 is root 3 over 2. Now you'll notice I did not lose that 4, and so we'll distribute that through. So we end up with 2 sine 3x plus 2 square root 3 cosine 3x. So there's some things I want us to notice here. Notice the 3x does not leave. It stays visible. Also notice that there's a relationship between this, that's not what I want, between the 2 and the square root 3 over 2. And that relationship comes from the fact that these are both multiplied by a sine and a cosine of the same angle. So it turns out that 2 squared plus 2 square root 3 squared, if I did that, equals 16, which is 4 squared. And those numbers all appear here, right? So there's the 4. So this number squared plus this number squared is always going to equal that number squared. And even more importantly, or as importantly rather, this 2 comes from this 4 multiplied by the cosine of my second angle. So the 2 is equal to the 4 times the cosine of the pi over 3. And the 2 square root 3 is equal to the 4 times the sine of pi over 3. Okay, so what this all leads to is there's a pattern here. And whenever there's a pattern in mathematics, we can develop an algorithm. And I'm going to come back in another video and we're going to do that. So stay tuned. Watch the next video for the punchline of this particular conversation. All right, we'll talk to you soon.